Well, let's jump right in. Today, we are completely demystifying Git internals. We're going to crack open that black box and give you literal X-ray vision into exactly how Git actually stores your code under the hood.
But before we get to the good stuff, let's talk about a feeling we all know a little too well. You know that visceral panic that hits when a terrifying Git error pops up right before a strict deadline? You're right in the middle of a rebase and suddenly Git starts yelling at you about detached head states, missing objects, and flat out refusing to apply some random string of characters like F3A 9C12. It's incredibly intimidating, right?
So it really begs the question, what is Git actually doing to your repository in those moments? Is it some kind of dark magic? Is it literally destroying all your hard work? Well, I promise you it's neither. By the time we wrap up this explainer, those scary errors won't look like ancient curses anymore. They'll just read like simple, logical, and highly predictable instructions.
Okay, let's dive into this because to actually conquer Git, we need a fundamental shift in our mental model. Git is not magic. At its very core, it's literally just a simple content addressable store. Think of it like a giant basic key value database. The key is a unique mathematical hash of your file's content, and the value is the content itself. That's it. Everything in your project history is stored exactly this way.
And because of the specific design, Git has a few ironclad rules that basically guarantee it never loses your data. First up, the exact same content will always generate the exact same hash, no matter what machine you're on. Second, if you change even a single character, boom, completely different hash. And third, these objects are totally immutable, meaning when you change a file, Git doesn't overwrite the old object. Nope, it simply creates a brand new one. Now here is the absolute best part. Git's entire universe is built from just 4 simple object types. Seriously, that's the whole shebang. Every branch, every merge, literally every piece of code you've ever written in Git is constructed from blobs, trees, commits, and tags. If you can wrap your head around these 4 puzzle pieces, you understand exactly what Git is doing behind the scenes. Now, what's really interesting about this is the difference between a blob and a tree. A blob stores purely your raw file content. We're talking just the bytes, no file name, no path, nothing else. The tree object, on the other hand, acts kind of like a directory. It's basically a list that maps your file names to those underlying blob hashes. And because they're separated like this, renaming a file in Git is completely free. The heavy, data-filled blob stays exactly identical, while only the lightweight tree updates the file name. Pretty smart, right?
So how does Git actually calculate those crazy 40-character SHA-1 hashes we see everywhere? Well, it's just simple math that applies to every single object type. Git simply takes your raw content, slaps a small header on the front, which just says the object type, like blob, tree, commit, or tag, adds the file size, a null byte, and then runs that entire package through a cryptographic algorithm.
But hey, don't just take my word for it. Using just a couple lines of Python, we can manually combine the word blob, the size, and the text, and compute the exact hash Git uses. No Git commands required. And the real secret here? To hash a commit, tree, or tag, you literally just swap out the word blob for the other object type and pass in its text data. It's pure, mathematically verifiable integrity.
Let's move to the terminal and see how this actually builds, simulating a look directly into that hidden .git directory. If we use the command git catfile-p on a commit hash, we can literally read the raw object and look at what a commit actually is. It's really just a tiny text file. It lists a tree hash, a parent commit hash, your author details, and your commit message. That's it. Okay, let's peel back the next layer of the onion. If we take that tree hash from the commit we just looked at and run git catfile on it, we see the directory mapping. It gives us file permissions, object types, hashes, and the actual human-readable file names we recognize. So the commit pointed to this tree, and now this tree is pointing us directly to the blobs.
And finally, we reach the very center of the onion. By inspecting one of those blob hashes, we see the actual raw text data of our file. In this case, simply #learning-portal. This completely proves that all your complex Git commands are really just navigating a simple, logical structure of text files pointing to other text files.
Let's lock this knowledge in by actually building out the visual graph of your repository step by step. Our foundation, step 1, is always the blob. It sits right at the bottom, securely storing your raw file content as an immutable, content-addressed hash. Then, step 2 brings in the tree. The tree acts as the structural wrapper. It points directly down to that underlying blob and gives it a file name and a specific place within your project's directory hierarchy.
Step 3 is where time actually comes into play. The commit object simply wraps the tree. By pointing to a specific tree and adding an author, a timestamp, and a commit message, the commit essentially captures a permanent, unchangeable snapshot of your entire project at that exact second in time. And finally, step 4 completes our graph with the tag. A tag is really just a convenient human-readable pointer, something like version 1.0, that points directly to a specific commit. As you can see, this entire beautiful chain is really just a linked series of physical, immutable files sitting right there locally on your hard drive.
And this brilliantly illustrates the absolute biggest misconception out there about version control. A lot of people assume Git stores diffs, just a list of the changes from one commit to the next. But it absolutely does not. Git stores complete snapshots. If a file doesn't change between commits, the new tree just points to the exact same already existing blob. It deduplicates everything automatically, which is exactly what makes branching incredibly fast and cheap.
Now you might be wondering, well, if Git saves full snapshots every time, wouldn't a massive repository take up, like, terabytes of space? Enter pack files. In the background, a process called git.gc uses a brilliant delta compression mechanism. It seamlessly combines thousands of loose object files into a single, highly compressed file. This ensures your massive repository stays remarkably small without breaking that elegant object model we just talked about.
So let's loop back to our original problem at the start. Look at that big, scary, detached head state error now. With your new X-ray vision, you know head is literally just a text file. The translation? A detached head simply means that file currently contains a raw commit hash instead of a branch name. That's it. It's not a failure, it's just a state. You can safely look around or just check out a branch to reattach it. No panic necessary.
So the crucial takeaway here is that Git is always just telling you exactly what is happening to the object graph. That terrifying could not apply F3A9C12 rebase error. Translation, Git was trying to replay a specific commit object onto a new parent tree, and the underlying blobs at the same path were mathematically incompatible. In plain English, it's just a simple file conflict.
You now know that underneath it all, Git isn't some complex web of dark magic. It is a beautifully simple system of blobs, trees, commits, and tags. So I leave you with this challenge. Next time you see a scary Git error pop up on your screen, are you going to panic? Or are you going to use your new X-ray vision to simply read the object graph? You have the tools now. Go use them.